Hello dear students, today is the second lecture for mathematical statistics subject. As we mentioned in the last lecture, the expected value of a random variable result in the following theorems. Let x be a random variable with probability distribution f of x. The expected value of the random variable g of x is mu g of x equal expected value of g of x equal summation gx times f of x if x is a discrete. Mu g of x equal expected value of g of x for equal integration from minus infinity to plus infinity for g of x times f of x dx if x is continuous. For example, suppose that the number of cars x that pass through a car wash between 4 p.m. and 5 p.m. on any sunny Friday has the following probability distribution as in the following table. Let g of x equal 2x minus 1 represents the amount of money in dollars paid to the attendant by the manager. Find the attendant's expected earnings for this particular time period. The solution: by theorem 4.1, the attendant can expect to receive expected value for g of x, expected value for 2x minus 1 equal $12.67. Another example, let x be a random variable with density function f of x, x squared over 3 and x between minus 1 and 2 and f of x equals 0 elsewhere. Find the expected value of g of x equal 4x plus 3. By using theorem 4.1, we have expected value for 4x plus 3 equal 8. We shall now extend our concept of mathematical expectation to the case of two random variables x and y with joint probability distribution. The definition: let x and y be random variables with joint probability distribution f x and y. The mean or expected value of the random variable g x and y is mu g x and y equal expected value for g x and y equal summation x summation y g x and y times f x and y if x and y are discrete, and mu g x y equal expected value for gx and y equal integration for x from minus infinity to plus infinity, integration for y minus infinity to plus infinity for gx and y times f of x and y dx dy if x and y are continuous. Generalization of definition 4.2 for the calculation of mathematical expectations of functions of several random variables in straightforward. For example, let x and y be the random variables with joint probability distribution indicated in the following table. Find the expected value of gx and y equal x times y. The table is reprinted here for convenience. The expected value for x times y equal 3 over 14. Another example, find expected value for y over x for the density function f x and y equal x times 1 plus 3y squared over 4 for x between 0 and 2 and y between 0 and 1, 0 elsewhere. The expected value for e over x will equal 5 over 8. Note that if gx and y equal x, in definition 4.2, we have expected value of x equal summation x summation y x times f of x and y equal summation x x times g of x for discrete case, and the following formula for continuous case, where g of x is the marginal distribution of x. Therefore, in calculating expected value of x over a two-dimensional space, one may use either the joint probability distribution of x and y or the marginal distribution of x. Similarly, we define expected value for y as expected value of x. Now we have new topic. It is the variance and covariance of random variables. The mean or expected value of a random variable x is of a special importance in statistics because it describes where the probability distribution is centered by itself. However, the mean doesn't give an adequate description of the shape of the distribution. We also need to characterize the variability in the distribution. In figure 4.1, we have the histograms of two discrete probability distributions that have the same mean, mu equal 2, but differ considerably in variability or dispersion of their observations about the mean. The most important measure of variability of a random variable x is obtained by applying theorem 4.1 with g of x equal x minus mu square. The quantity is referred to as the variance of a random variable x or the variance of the probability distribution of x and is denoted by variance x, or symbol of sigma square x, or simply by sigma square, when it is clear to which random variable we refer. The definition: let x be a random variable with probability distribution f of x and mean mu. The variance of x is sigma square equal expected value of x minus mu square equal summation of x for x minus mu square times f of x if x is discrete, and sigma square equal expected value of x minus mu square equal integration from minus infinity to plus infinity for x minus mu square times f of x dx if x is continuous. The positive square root of the variance is sigma is called the standard deviation of x. The quantity x minus mu in definition 4.3 is called the deviation of an observation from its mean. Since the deviations are squared and then averaged, sigma square will be much smaller for a set of x values that are close to mu than it will be for a set of values that vary considerably from mu. For example, let the random variable x represent the number of automobiles that are used for official business purposes on any given work day. The probability distribution for company A in a figure 4.1a is as in the following table, and that for company B is as in the following table. Show that the variance of the probability distribution for company B is greater than that for company A. The solution: for company A, we define that mu A equal expected value of X equal 2, and then sigma square for A equal 0.6. For company B, we have mu B equal expected value of X equal 2, and then sigma square for B equal 1.6. Clearly, the variance of the number of automobiles that are used for official business purposes is greater for company B than for company A. An alternative and preferred formula for finding sigma square, which often simplifies the calculations, is stated in the following theorem. Theorem 4.2. The variance of random variable x is sigma square equal expected value of x square minus mu square. The proof: for the discrete case, we can write sigma square equal summation x for x minus mu square times f of x equal summation x for x square minus 2 mu x plus mu square times f of x equal summation x square f of x minus 2 mu times summation x times f of x plus mu square times expected times summation for f of x. Since mu equal summation x times f of x by definition, and summation f of x equal 1 for any discrete probability distribution, it follows that sigma square will be equal expected value of x square minus mu square. For the continuous case, the proof is step by step the same, with summations replaced by integrations. Example: let the random variable x represent the number of defective parts for a machine when 3 parts are sampled from a production line and tested. The following is the probability distribution of x, as in the following table. Using theorem 4.2, calculate sigma square. Solution: first we compute mu equal 0.61. Now expected value for x square equal 0.87. Therefore, sigma square equal 0.87 minus 0.61 square equal 0.4979%. Example: the weekly demand for a drinking water product in thousands of liters from a local chain of efficiency stores is a continuous random variable x having the probability density f of x equal 2 times x minus 1, and x is between 1 and 2, 0 elsewhere. Find the mean and variance of x. To find the mean, we have to calculate expected value of x, and to find the variance, we have to find the expected value of x and the expected value of x squared. And we find that mu equal 5/3 and expected value of x squared equal 17/6, and the sigma square is 1/18. At this point, the variance or standard deviation has meaning only when we compare two or more distributions that have the same units of measurement. Therefore, we could compare the variances of the distributions of contents measured in liters of bottles of orange juice from two companies, and the larger value would indicate the company whose product was more variable or less uniform. It wouldn't be meaningful to compare the variance of a distribution of heights to the variance of distribution of aptitude scores In section 4.4 we show how the standard deviation can be used to describe a single distribution of observations. We shall now extend our concept of the variance of random variable x to include random variables related to x. For the random variable g of x, the variance is denoted by sigma square g of x and is calculated by means of the following theorem. Theorem 4.3. Let x be a random variable with probability distribution f of x. The variance of the random variable g of x is sigma square g of x equal expected value of g of x minus mu g of x over square summation of x for g of x minus mu g of x square times f of x if x is a discrete, and the following formula if x is a continuous. The proof: since g of x is itself a random variable with mean mu g of x as defined in theorem 4.1, it follows from definition 4.3 that sigma square g of x equal expected value for g of x minus mu g of x. Now applying theorem 4.1 again to the random variable g of x minus mu g of x square completes the proof. For example, calculate the variance of g of x equal 2x plus 3, where x is a random variable with probability distribution as in the following table. The solution: first we find the mean of the random variable 2x plus 3 according to the theorem 4.1. The mu for 2x plus 3 equals 6. Now using theorem 4.3 we have sigma square for 2x plus 3 equal 4. Thank you.